I think this is the first time that I'm attending this seminar, even though I've been here for a year already. I didn't realize when we present, my first seminar. I think would be attending one of the seminars before, but I think the first year was quite easy learning, so now I can start with some more. The talk today is about neuro-symbolic AI and neuro-symbolic systems. The title says an overview. So I have to say something. I'm not an expert in neuro-symbolic AI. I've done some work. I've written a few papers on that, but by no means I'm an expert. My background is in symbolic AI. It's what I've been doing the last 10 to 12 years. But before that, I did theoretical computer science. So I'm mostly interested in foundations of computer science. I'm very interested in logic, connections with game theory, and applications in different domains of computer science. And one of those is artificial intelligence and multi-agent systems. So up until probably 5 years ago, I had done any work on learning systems, but then I had to teach that. So I had to learn. and anyway, I was being bombarded like everyone with all these things about neural networks, and we never get funded if you don't do neural networks, things like that. So I started looking at not just neural networks, but learning systems, see if there were any connections with the work that I was already doing, the work that I like, and where I feel more comfortable. And then in that journey, I found this field called Neuro-Symbolic AI, which is the topic of today's talk. So the presentation will be like a brief overview of some of the models that are out there in this field. Also, we're going to give you the context and motivation of why this is important, why this is another field of AI that we should be thinking about, hopefully doing some work, and caring in general. Okay, so that was my way of saying if I make any mistakes, because I'm learning. Okay. So for today, probably the presentation will have three parts, sort of 1/3 of the full seminar will be dedicated to each of those. So at the beginning, some context and motivation. Then I will present some models and languages, and this is not a comprehensive overview or presentation of the field. So if you say, oh, look, I've seen this other system or model out there, most likely that's going to be the case, and most likely I won't have seen it. And then at the end, I will present some challenges and opportunities. So that last part is a little bit of what people working in the area think, and a little bit of what I see as new opportunities. So for the context, well, there are different subfields of AI, and probably you recognize these three, and mostly you work in one of these ones. You have, on one hand, symbolic AI, which is that set of approaches that use rule-based systems. They typically use logic, and is everything that we know under the big name of knowledge and representation. Those set of methods are quite good, quite effective when you have complete information systems. So you know absolutely everything. You can, with these systems, specify everything that you need, and then solve whatever problem you have in front of you. That's usually the case when the systems are not too big. And let's just leave it there. I don't want to be too precise on what I mean by too big, but let's say that symbolic AI systems are very good at reasoning and modeling these problems or systems where you have all the information in the system, but provided that they have a reasonable size. Then we have this other subfield of AI. It's called structural or relational AI. Typically, there you have what is known as probabilistic models or probabilistic graphical models, and it's very effective in reasoning about systems when you have uncertainty or imperfect information, but it is already measured or estimated in some sense. And what I mean by that is you have probability of something happening, right? So instead of having, like in machine learning, all your data there, let's say, unstructured and not analyzed, you have aggregated all that and you have put some measures on whatever what you have as your in the variables system. And then you have another field. The connection is of sub-symbolic AI, what most people just call machine learning. Some people even think about only deep learning and a very specific set of methods and techniques. And there is where you have all the methods that use learning. They typically work on raw data, and they are very effective when you have really noisy, messy information. It's all there in the data, but it's all unstructured. So if that is the case, typically it works quite well compared to these other two. By the way, when I say that they work quite well, I typically mean compared to the other approaches. So those are the usual three approaches or methodologies that you have at hand. You may be you may want to use one of those either because the problem seems like, this is the right thing to do, or this is the right thing to do, or this is the right thing to do, or maybe because that's your background and you have your big hammer and you want to smash everything with that hammer that you know how to use. Now, each of these techniques are good and bad at different things. So, for instance, symbolic AI, because it's based on logic and rule-based systems, they are quite good for reasoning. And typically what you do there is just logical inference, okay? Then you have here relational AI. As I said before, it is good to model uncertainty explicitly, okay? And you can also do reasoning, but in this case, because you have probabilities all over the place in these settings, you do probabilistic inference. And then here, for the sub-symbolic AI approaches, you have different techniques that are quite good at approximating a solution. There are no explicit inference methods in this case, but you can do a lot that is not necessarily direct or explicit inference or reasoning. For that. So, I mentioned that what is what they are good at. And if you start looking at what they are not very good at, you usually go to the other fields. So this is not very good at reasoning, well, this one is. This one is not very good at handling incomplete or imperfect information. Well, this one is. And then you have this one in the middle that with which you can also find these implementary properties. So it is very obvious what are the strengths and the weaknesses of the different methods. And so many people know it and have seen it. And some said, well, it would be great if we could mix some of these different approaches with the hope that we adapt the strengths and mitigate the weaknesses rather than the other way around, of course. And that's how Neuro-Symbolic AI came to play. It is a field in which you want to integrate learning with reasoning, and typically you can do it in two different ways. You can do it by extending learning systems, so think of a neural network or a reinforcement learning system with some symbolic knowledge somehow. Or you can do it in the other direction. You can do it by adding some learning components to some symbolic AI system that you already have. Yeah.
So I was just wondering, where are you placing generative AI in your three-way split?
I would say it is more on the connectionist part, but again, as I said, this is not, this is part of the picture, and there are many things that are not put in here. Yep.
What kind of knowledge are you talking about when you talk about symbolic knowledge? What kind of code does that input?
For instance, you want to build a controller. Okay, nowadays building controllers, one of the techniques that you can use is use learning, reinforcement learning or something like that to build a policy that behaves like a controller. You could simply take the system and then make it interact with your environment and build your RL system in the old-fashioned way. But you may also know different things about the environment, information that is not necessarily information that is explicit in the data. Like you need a control for a robot that is going to be moving in a space like this. And it is the case always that at the end of every corridor, I don't know, there is a toilet or something
like a hazard to avoid or something like that.
Yeah.
You might code that in as symbolic knowledge.
Yeah, exactly. It's something that if you make the system interact with the environment, eventually, hopefully, you will learn that that's the case.
Yeah.
But in many situations, if you already have the knowledge, there is really no need to make the agent learn it. You can just incorporate all that knowledge already. So that's just one example. We will see that there are other examples where you may want to incorporate symbolic knowledge or different type of knowledge that you already have for your environmental system. Now, why do you want to do this integration? As I mentioned before, because when you look at the strengths and weaknesses of these different paradigms, you find these complementarities. So, symbolic AI, good, for instance, for property checking and assurance. Why is that? You have logic. That's what you do when you have logic, you prove properties, or you can prove properties. You can do formal reasoning, and it is very explainable. You look at the system, why some inference is made, what are the rules that support that inference, and that's it. You understand why the agent is doing what it is doing. On the other hand, when you have sub-symbolic AI, you know that these systems are quite good for pattern recognition. You know that they can process information very well under uncertainty, and you know that they can deal very well with large data sets. If I were to mention the weaknesses of this other paradigm, I will be talking about the same things that I have here. So why do we want the merge? Because they seem to be complementary techniques. Now, how we do it? Well, that's what we are going to be seeing in the next slides. And I'm going to present a few models or architectures and languages that are typically used by people who are working in this area. Now, who are those people? Well, they are all over the world, but again, just to give you some context, in the Alan Turing Institute, there is an interest group precisely in Neuro-Symbolic AI. So that's a small subset, but there are quite a lot of people in the UK interested in that. The academics, all of us, so there are there have been at least 3 Dutch tool seminars where the focus is Neuro-Symbolic AI, and there is other one coming in 2026 in the summer. So 4 Dutch tool seminars already focus on this, showing the interest, at least, of the academics in this topic. Big companies are also interested in this, and they even want to share or have more people working in this area. Proof of that is, for instance, this a summer school and a number of seminars and workshops that have been sponsored by IBM. I mentioned that one in particular. It's not the only one, but I mentioned that in particular because they typically invite Turing Award winners and people like that, and to give talks about the importance of merging learning and reasoning. You can also find workshops collocated with typical AI conferences like Ishkai, Triple AI, that. The big companies are interested in this. So I'm sure that you all know AlphaGo. So AlphaGo is one of the systems that is a Neuro-Symbolic system. In Amazon, here in the UK, for instance, we have the work by Byron Cook, which I personally think is quite good in the area. Again, the guys in IBM, and there are many other research organizations. Mentioning here DARPA in particular because I'm also involved in one of the projects there about learning and reasoning. So this is to say, lots of people are interested in this topic, and that goes from the academics, students, people with probably little access to money, down to big companies putting millions and millions and millions of pounds and dollars into this. Okay, what I'm going to present next is the main models and languages that I found for Neuro-Symbolic AI. And I would say this is a summary of the information that is mostly contained in these 3 surveys. If you go there, they will say previous service. So from those 3, you can get to 3 more. So you can get like 9 or 10 surveys on all of it. Probably these ones are good because of the dates. The other surveys are 2020, 2015, 2016, and even before that. But most of the material that I'm going to present here is contained in this. And I guess you will share the slides so you will be able to have the referencing if you want to learn more about it. Okay, so we're moving now towards the second part of the seminar. No more, well, this is the last slide of context and motivation. That which will how do we produce a new Neuro-Symbolic model or architecture? Well, the way it's being done so far is by looking at what are the parts or components that you have whenever you have a symbolic or a reputational AI system, and what you have when you have a sub-symbolic AI system. So if you have a symbolic AI system, typically you have, think of a SAT or SNT solver. You have set of variables, you have some rules, and you have some relations, and based on that, you have very clear algorithms that go and then hopefully solve the problem that you have. For sub-symbolic AI, you typically have data sets, you have a loss or a reward function, depending on whether you're working with neural networks or if you're working with reinforcement learning. And then you have an architecture there, right? Some type of neural network or some specific type of reinforcement learning system. What is what we do, or what is what most people working in this area have done? What they do is they take some of these components or parts, and either they redefine it or just pre-process it or process it completely using a technique that comes from the other paradigm. So if you have, for instance, here a symbolic AI system, you may say, well, I have my variables, I have these rules, and I have these relations. I'm going to take these rules, and instead of producing them explicitly, I'm going to generate these ones using one of these systems. So that would be one of the possible situations. Or here, you may say, well, I have my set up my neural network, and the loss function is defined in this way. So what I'm going to do is I'm going to use one of these symbolic AI systems to define this loss function or to define the reward function. Why? Because hopefully that will incorporate some symbolic knowledge that you have. And why do it that way? Because possibly by using these systems here, you will be able to handle uncertainty better. So there are different motivations. So the general approach is typically take your system, find one of the components, a subroutine, a part, some aspect of the system, and then change it for some engine from the other method, type of methodologies, or don't change it but process it somehow. And yes, extract some information from that you already have. Of course, you can do that in many different ways. So I'm going to present here a number of those that more or less summarize the main approaches that are out there for neuro-symbolic AI. So one is having synthesized architectures. Now, what is that? You always have these two. One is when you start, let's say, in the neuro part and end up in the symbolic part, and the other one is typically when you start in the symbolic part and you end up in the neuro part. So for the in the first case, you may have a neural network or a formally learning system that is generated from a symbolic logic specification. What is what you typically do? You use a logical language. Can be first order logic, can be a fuzzy logic, or it can be a probabilistic logic. And then using a process of synthesis, which is finding models for that formula or for that logical system, then build your neural network or build your reinforcement learning system. Once you have that, that is what you use then for the processing of information. So this is one of the most decoupled ways of doing neuro-symbolic AI, which is simply use one to generate the model in the of the other kind, and then just use the other one. Forget about what you did before. The other approach is generate a set of rules in a rule-based system, an expert system, using neural network architecture. What is what you do? Typically, you take the data, you start identifying patterns such as things that can be related to existential quantifiers, things that can be related to universal quantifiers. That, of course, has a connection to conjunction, disjunctions, and all that. And then, based on that, generate your rule-based system that is now the one that you are going to use to do reasoning. Okay. So this is the first type of systems. It's very simple. It's just take one of these types of AI to generate a model of the other type. So very little interaction in this case. The system that is generated usually simulates what the original system would do, in the sense that if you here started with a logical specification, and the logical specification will give you some output based on certain input, then the neuro system should do precisely that. Okay, you give to a neuro system the same type of input, then the output, membership in some class, if you're doing classification, should give you something similar. Okay, so this was the first type. Second type, sequential or horizontal architectures. In this case, so if you can see, there was some ball here because I wanted to indicate that that system in ball is the one that you were using later on. Here for this one, you actually use both systems. So you have a component that does some symbolic reasoning on your input data. Then the output is put into a neural system, and then you have your output. In some cases, you probably want to take this one also as the input of another symbolic system to have your output. Or you may do it the other way around. Take data, process it, use it, a neural network, for instance, and then the output, use it to do reasoning on that. So in this case, unlike the previous one, you actually use both systems. You are not using one to generate another one. You take your data, your input, put it through one of the systems, process information, then get an output, and then that output feed it into the second system. And you can do it either way. So that would be the second type of architecture. Again, very, very loosely coupled. It's like just having two components there that probably would not deserve to be called architectures of a neuro-symbolic system because there is really not much interaction between them. One example of those systems is deep prof. So this is one of the languages and systems that have been gaining more traction in the last few years. Is of this kind the neuro-symbolic type, meaning some information, some data will be processed by some learning system, and that is going to be used as the input of this symbolic system. So for deep prof, what is that symbolic system? It is a probabilistic logic program, which is a logic program where the statement, the assertions can have some probability. Okay, that's all it is. So in deep prof, the extension that they propose is that those probabilities that you could probably hardwire are actually coming from data that is being analyzed by neural network. So at the end of the day, you have a logic program with some annotated probabilities, and all the computations will be done at that level. Only that those probabilities came from data that was analyzed previously by the neural network. So that's all is done there. How that looks like in practice, if you ever taken a course on Bayesian networks or computation, you probably recognize this kind of graph here. This is a typical example that says you have an alarm. The alarm may sound if there is a burglary or if there is an earthquake. And there are two people here, John and Mary. And if Mary hears the alarm, then she will call the police or some services. And if John hears the alarm, then we'll make a call. If you were to model this type of system using probably a probabilistic logic program, you will get something like this. I don't think you can read it from the back, but essentially, this is a logic program, usual logic program. The only difference is that here at the beginning, some of these assertions have a probability of happening. So 0.1, 10% for burglary, 0.3, so 30% for if the alarm Mary, and 5% that there is an earthquake, and 60% that John hears the alarm. And based on that representation, you could just go and do probabilistic inference and ask questions, the typical question that you would ask if you have a Bayesian network, okay? Which is, what is the probability that, that's great. Typical questions like, what is the probability that this happens, or if there is a probability that this happens here, then what is the probability that they are, and things like that. What is the new element? The new element is this one here. So these probabilities that I'm putting in the very beginning, if I were to use Bayesian network, for instance, or a probabilistic logic program in this case, I can say that they are coming from data that is analyzed by a neural network. So I have here this neural network and this neural network that will give a value, this probability, to these events happening, that there is a burglary or that there is an earthquake. Everything else is pretty much the same, only a little bit of changing the syntax, but everything else is precisely the same. Yeah.
So Why do you need a neural network at this point if it's just a fixed probability, or does it change based on some input data?
Because it may be that, I mean, you could, for instance, go analyze all the data, get these probabilities here, and then put them there. Or you can think that this data is being analyzed, that is not obtained since the very beginning, that you need the neural network to do this job of getting these numbers.
Or if
Well,
it's not observed the amount of burglaries or the amount of earthquakes?
Yeah, exactly.
Trying to infer it based on the occurrences.
Exactly. Yeah.
Um,
So that's one of the is one of the ways of doing this type of neuro-symbolic reasoning. You know, from a high level point of view, this is just again a logic program that can reason with probability, so you can do probabilistic inference. And here you only have a little bit where it says I can, in addition to that, get those probabilities from the workings of a neural network or some learning system, given that I have some input data. Okay, this is another type of systems. They are now top-down systems, and they typically use the other type of framework within one of these components. And that component is seen as a black box, like an oracle that you can query to do something.
And what do you call a neuro oracle? What does that mean?
Oracle is another word for black box. You just simply ask a question, give me this, this is the input data, give me the answer for this question, and then you get the answer, and that's it. You don't.
Okay, so it's like a kind of like a place where the answer comes from.
Yeah,
Okay.
they come from, and you, as the person or the agent asking the question, you don't care how that is produced.
Okay.
So again, you have two types. You have a symbolic system that have some neuro oracles. So it's a typical symbolic system where in some part of the process, you will be asking a neural network or another system a question. One of the examples there is, for instance, AlphaGo. AlphaGo is a system that does Monte Carlo research, but it uses a neural network for heuristic evaluation. So from a high-level point of view, AlphaGo is just simply another Monte Carlo research algorithm. The efficiency is in the fact that instead of computing these heuristics, which is something that is quite expensive, for Go, for instance, they use this kind of oracle where you have all the pre-processed information, and so that very quickly you can go and ask, is this a good move? Yes, no. And the system just goes and tells you the answer immediately. So this is one of the ways of doing that. Essentially, having one of the two systems dominating and just using the other type of system as an oracle, as a subcomponent or as a subroutine. Yeah.
Would you mind just briefly explaining Monte Carlo tree search for the benefit of some people who might not come across it?
So that's an algorithm in which you get some samples, okay? And based on those samples of the environment, can be states of the system, states of the environment, different behaviors, you make a full picture of what the system may look like. Is an algorithm that allows you to have very good estimates of different values of variables in different states of a system when the state space is just too large. Okay.
So like chess with all the different potential positions and pieces on the board.
You can use it, yeah, all the positions in the board will be one thing, and then you can just go and say randomly, what if I'm in this position of chess? What happens if I do this? And now another random position of chess, this other one, or in this case, will be for Go. what if the state of the system is this one, this configuration in code? What is the best thing to do there? So it's just randomly generating different positions and analyzing locally what happens there. If you make a big enough sampling of your state space, you can have a pretty good estimate of the whole thing. Okay, so this is one of the systems, and I have to say, if you're coming from a symbolic AI background or belong to a symbolic AI community, this is one of the easiest to start with because you're still in your comfort zone, you're still with your symbolic AI systems, and you can sometimes close your eyes and say, I know that there is a network that is processing information and just giving me this information. You know, it's my slave. I said, give me this value, and you get it, and you simply use the value. Then you have the other type of systems, again, where we run a neuro or an RL system with some symbolic oracles. What is an example of that? For instance, if you are doing reinforcement learning, you might have your reinforcement learning with a symbolic component or mechanism that is telling you what is your reward function. Why that example is interesting, I think, because designing reward functions, designing good reward functions is quite complex for RL systems. And sometimes the better your reward function is, hopefully the better your system will be. So that's another way of doing it. So in this case, the takeaway message is having a symbolic oracle is a component of a neuro system, or a neuro oracle is a component of a symbolic system.
To give an example of the symbolic reward
Yeah.
function.
I have for each of these, apart from the first one, I have an example next. So I'm going to give you I call them models or architectures, but it is a very informal and high level presentation of this. If you go to the papers, you will see obviously all the details. But yeah, for each of those, I will have an example next. So this is an example of an RL system with a logic defined reward function. So in this case, for example, we're going to have a reward function that is defined logically. So there will be a logical language here to say what is the reward that an agent will have after interactions with the environment. Now, this reward formula, because we use a logical language there to define that, is going to be used to generate something that is called a reward machine. So it's the thing that I'm going to be querying to ask if I'm playing chess and I do this, what reward I get? You get this much. If I do this other thing, which reward I get? You get that much. And that's it. The reward machine is the device that will be telling me how good I'm doing when I'm training these RL systems. So the RL system queries the reward machine at training time. In doing this process, what we achieve is that at the end of the training process, the RL system will learn to respect that what is being encoded by this reward function. So it's going to respect the reward formula. Another advantage of using this approach to defining reward functions in RL systems is that it will allow you to define something that is called non-Markovian reward functions, meaning sometimes, and this is quite often the case in different terms that we have or in games, you do one thing and that thing that you do is neither good or bad. You need to do more for me to know if you're doing well or not. So you do one thing, let's say it's not that you don't get any reward because here you always get a reward, but let's say that you get a reward of 0. Could be good or bad in the end, but at that point it's 0. So you do one thing, then you do another thing, and another one, and another one, and another one. And then eventually after having done many things, maybe the sequence of all those actions is something good. So your reward machine will give you a positive reward there. And if that sequence of actions is actually not very good with respect to the goal that you want to achieve, then your reward function will give you a negative reward in that case. So that's why it's here it's a non-Markovian reward function, because it is not given in every state, it's given after you have seen a sequence of states. Yeah.
Is there a fundamental assumption here that the reward function has been programmed by a human expert?
Yes, I didn't say that, but typically those reward functions are engineered by an expert. Is a person who knows, let's say in a game, what are the rules of the game? You can encode that logically. Or it is a person that knows what are the, let's say, sequence of tasks that you need to accomplish in order to get a positive reward in the end. Okay. Okay, so more concretely, how that works, so what it looks like. And I told you that I done a little bit of work on neuro-symbolic systems. So this is part of this paper, which is one of those pieces of work that I've been involved. So that reward function can be defined logically, and in this case, you can define something like this using temporal logic. So this operator here means eventually, and this operator here means always. So what this thing is saying is that imagine that it is a robot that needs to visit certain locations. This one says, look, I want that the robot eventually visits location 1, and after that, eventually at some point visits location 2, and then after that, always it is either in location 3 or 4. Okay. So what this formula will do, once it is translated or converted into a reward machine, is keep track of what the agent is doing. In this case, just give 0 as a reward. And if the machine sees that the agent visits location 1, then location 2, and then always location 3 or 4, then at that point it gives a reward of 1. Otherwise, that's not going to be the case. It's going to continue giving reward 0 or then something negative or something like that. Now, how do we incorporate this in particular into a reinforcement learning system? We can use this formula to generate an automaton that satisfies exactly the same set of traces or brands or sequences of states that would be models for this formula. And then, given the automaton, give a reward of 1 if that run in that sequence of states is accepted, or 0 in every other case. So if you use this approach in RL systems, not only you define your reward function in a logical way, but also you make sure that after training, your RL agent respects that reward formula. Whatever property that you have encoded there in the formula is something that is going to be a goal for the agent to be achieved. Trying to do that, let's say manually, it would be much harder, and partially that would be much more difficult because this reward function is, in this one in particular, is not Markovian. So this is where we start seeing that using here some symbolic knowledge into the learning system really gives you things that you wouldn't easily get if you didn't have access to that. You can do these kind of things also with multi-agent systems. So you can assume that not only you have an agent, but that you have different what you call AI agents, each of them with a different goal of this kind. And then after training, all of them will always be trying to achieve that goal. Okay. So now the next set of architectures, I call them here embedded architectures. And again, we have the two types. One is you have a symbolic system where some parts of features are generated by a neural network. And the other one is you have your neuro or your RL system with some symbolic based features. For instance, it's sort of similar to the previous case. If you have a loss function, then you can define that loss function using a logical language and incorporate whatever it is that you define with the logic into the training process of your neural network. So here, what do you get? At the end of the day here, well, maybe one clarification in case it is not sufficiently clear. Here at the end, you have a purely symbolic system or a purely neural system, only that one of those purely symbolic or purely neural parts was defined using the other type of approach. In the previous case, you don't have that purely symbolic or purely neural system because you have, for instance, for RL, your RL system, but you also have your reward machine. Okay, so you don't embed the reward machine into the RL system. What you do is you keep it outside as an oracle. Here in this case, we're not keeping anything outside as an oracle. What we're doing is defining or converting something that is here, for instance, a loss function that you would typically use for a neural network system as a loss function, but only that is being defined using some logical language, for instance.
Julian, it's 9 minutes too, so
Okay.
you try and wrap up in the next couple of minutes.
Yeah, I will finish with this one and then move quickly. So this is an example how you would do that. Typically, if you are building or designing a neural network, you have your loss function. And in this case, if you want to incorporate symbolic knowledge, you will say that your loss function is your classification loss function, the one that you would typically use, plus some logic loss, meaning a penalty that you apply whenever the neural network is not satisfying those logical constraints that you added. Okay. So for instance, what is one constraint that you may want to add? You want to learn something from data, and this information, you want also this to be respected, that for every entity, if the network classifies that as a cat, it should also classify that as an animal. Now, this logic formula, you can give it a different semantics, where the true value go from 0 to 1, and then doing a little bit of mathematics. This is using a particular semantics for this formula. You can define explicitly what it would be the logic loss, the classification loss that comes from the fact that you classify whatever entity or input that you have instance as a cat or as an animal, that will be your classification loss, and then you use them together to have your total loss. So what you're doing here at the end is using simply a loss function that incorporates this information that you have here. Okay, languages, I'm not going to talk much about this one then. Basically, most of the literature you find is about systems that use logic programming and some probabilistic or deep probabilistic extension of those languages. Some of those are already integrated with Python, so you can build non-trivial systems like that. It goes back to the example that I had before. Now, back to the last part, research challenges and opportunities. So these are the main questions that we want to answer when we are working with neuro-symbolic system. One is how to integrate neuro-symbolic architecture. So there are a lot here. People keep coming up with different architectures, and the reason is there is no canonical model. It's not like in functional programming that everybody says, I don't know, lambda calculus, that should be the core model. And anything else that comes after the lambda calculus is fine. Here we don't have that kind of architecture. So in particular, I'm interested in looking at game theoretic models because it relates a lot to multi-agent systems, and one of the areas that have not been explored so far is multi-agent reasoning in the space of neuro-symbolic AI. So all these systems that I presented to you, apart from probably the only work that I did there, is for single agent systems. So multi-agent systems, not deal with much so far. We still wonder how to represent symbolic knowledge in neural network architecture. There are some ways of doing it, and I presented a few, but again, there is no one definite way of doing it. This one here, how to make neuro-symbolic systems safer and more reliable, that has to do with the question of how, since now we have systems that have learning components sometimes, symbolic components, how do we do verification of these systems? We know how to do verification of symbolic systems very well, but how do we do when we have this other more continuous part that include the learning components? And here at the bottom, what about multi-agent systems? Is an area that has not been explored so far. So some people here will be working with me on this. One of the students is going to be focused on logic and logic foundations for neuro-symbolic systems, but in particular, multi-agent extensions of those architectures. And the other student is going to be focused on game models and semantics for this type of systems, again, in the context of multi-agent systems. And they are starting the PhD, or they started the PhD last month. So hopefully we have very fun 3 to 4 years together. And that's it. Again, as I said, I'm not an expert on this. I'm learning. If you have questions, suggestions, comments, anything is all welcome. I'm genuinely interested in this. I really think that the future of AI is through the combination of symbolic and sub-symbolic AI. And definitely, we still don't know what are the models and the techniques to deal with these type of systems. We have seen already great success of some of those, like AlphaGo, but those great successes are by people who have lots of money, lots of resources, and it would be great to be able to build systems that are reasonably small, but that can solve very challenging problems. I don't think we still have the techniques, the logics, or the architectures to do that. Thank you.
So, although, yeah, we've got to just about 2 o'clock, we do have the room booked for a bit longer. If people have questions and they would like to ask them. Yeah.
Thank you.
You wait 1 second.
Yeah.
So thank you very much for a really clear overview of what you're working on. I was wondering if you could clarify one part for me, which is how logic can be used to augment, let's say, a loss function to train a neural network. And so you gave the example of a sample being classified as a cat, but you also wanted to classify it as an animal as well, right? So in what way does this logical relationship provide advantages over, say, multi-class labels in a traditional neural network approach, where you assign a sample 2 labels, use the percentage loss?
Yeah, here the advantage is that you get an extra penalty because you can have the two categories and have different classifications there, and let's say work with that. But here, the advantage, at least from my point of view, is that you have this additional way of adding penalties when your system is, let's say, classifying an entity very well as a cat, but not as well as an animal. So the classification in one of the categories should imply the classification in the other category, and you can do that directly by changing the loss function. That's the way I see that it is an advantage. Now, is it the best way of doing it? I don't know. But it definitely gives you another alternative. Now, I present an example here, which is just that one single formula. But you can put there anything that you can express in any logic that you choose. It doesn't have to be first order logic, by the way. It can be some other language that is very good for expressing very intricate properties that are not just about classification. So that's where I see the value, the advantage, that it this alternative, this opportunity of doing things differently. In that particular case, by adding penalties to the loss function.
So in that example, it gives you a bit more flexibility to control the magnitude of the loss that you would incur if you don't correctly classify both of those labels, compared to just having a multi-label case where you've got 50% labeling correct and 50% incorrect. When you're using this kind of a logical regularization on the loss function, let's say, then you can increase the magnitude of that loss.
Yeah, that's one thing. Another thing that I forgot to mention, and I think it is important, is that another reason why we want to use neuro-symbolic systems is because we want to make them more explainable. So if you know that you're training a network with those constraints, you can, you know better why they're being trained towards whatever network you get in the end, because they are trying to respect or learn to satisfy those properties. So that's another reason that is completely unrelated to this. It's just about explainability. You can say, look, these are the set of rules or constraints that my agent is learning. So whatever decision is making it because this is what it was programmed to learn to do.
I don't really see how that affords much explainability. I mean, it makes the problem slightly better specified because you have this extra regularization, but I don't really see that as explainability. It's just another thing to shift it towards the right direction.
I guess it is, at least from my point of view, it's explainability in the sense that you know why some component of the system is designed in that way. For instance, I could, for the other example, the reward machine, I could try to design a very complex reward machine, or not reward machine, very complex reward function that, let's say, does the same. Not a different way, but does the same. But if instead of that, I have the logical formula, or even the automaton. An automaton is fairly simple to understand. Just the automaton saying, look, this is what the agent is trying to do. This is what it's learning. It is learning that it should always, at some point, visit this location, then that location, and that location. That's why it's behaving in this way. Okay. So I guess what I'm trying to say is, it gives you more information about why certain components of the system are designed in the way that they are designed, because you have a language that is telling you explicitly, look, this is what I want the agent to do.
And extending that, has there been much discussion about ethical AI and bringing in human principles, if you like? Is this a way that are people considering this as a way of stopping the black box running wild by putting these constraints on?
These constraints, good point. again, I think it gives you another alternative to do that. I have seen some work on, ethical AI or ethics in AI. And some people wanted to define logical theory that would ensure, let's say, fairness or certain properties that you hope that logically could be stated unambiguously.
Hmm.
Again, to me, it's just the idea that this will give you an alternative to do that, from my point of view, more clearly. You know exactly what you want, and then if you have your set of rules or actions or formulas, you can prove property and say, look, if my agent learns these things, then I can prove that it also learns these other things. Why? Because by logical reasoning, these things imply. And I know that my agent respects this set of rules. And therefore, every other probabilistic inference that you can make based on that. Yeah.
Thanks for the seminar. I didn't have much idea of symbolic anything beforehand, so really can see that. It's really open discussion, which is nice. Might be a naive question with that preamble, but given that a lot of what you're calling machine learning or non-symbolic systems are inductive, does that limit what you can do in terms of their interaction with logical reasoning?
Can you tell me more? I don't understand why you think that it will limit the interaction.
So,
I mean, there are fundamental challenges in making these interactions, but why what you're saying, you see it as a fundamental limitation for the interaction?
I mean, are you just limited to inductive reasoning then, if you're using machine learning?
Yes, but that's also why you want to put symbolic reasoning somewhere else. Not necessarily on top, before, at the bottom, but it's just to expand the possible reasoning capabilities that you may have. I also put in one of the slides at the beginning that with neural network, you don't have explicit reasoning mechanisms. That was because it's not that you cannot reason when you have a neural network. There is some reasoning that you can make, but it's not the kind of reasoning that you do with symbolic AI, with rule-based AI, or with, in general, with logic. So I don't see it as a limitation. I see it as just one side of the coin. And we could say the same about symbolic AI. For instance, it is well known that symbolic AI is not very good when you have very, very, very large systems. And you could say, well, then it is going to slow down the other one. Again, it's not the way I see it. I guess if you use it cleverly, hopefully, it would not slow down the other system by much. And instead, you would gain a lot more in the process through the integration. To me, the important question, like for me, is what is the most effective way of integrating these things? I mean, you could see from the slides that I presented to you, some of these integrations are really, really trivial. Use this system, that's it, go home. It doesn't sound or look like much of an integration sometimes. And I don't think there is an architecture that really integrates the two fully, or in a way that is really something that people will say, I think that is the right architecture to use. I guess in many cases it's also very problem dependent. Some architectures may be better for certain type of problems and not as good for some others.
So yeah, it's a great overview of hierarchy, a lot of which I was unfamiliar with, similar to Peter. But it feels like some of these approaches are predicated on the neural networks being able to learn as we expect them to, be able to generalize, and being able to deal with domain shift, all these kinds of problems which are fundamental to some of the big picture problems we have. And also reasoning under uncertainty, neural networks tend to be very overconfident compared to probabilistic graphical models. How do you think this is quite big question, but how do you think Neuro-Symbolic, I guess similar to Paul, how can it help us to resolve some of these issues, like these limitations in neural networks?
This limitation, I think the more grip you have on the design of these different components of a neural network system, the more you can use different reasoning techniques to give guarantees from the. I think, as I said, I come from a symbolic AI community. One of the main criticisms is usually like, that's not reliable. Sometimes that's how we want to justify what we do. You know, we do formal reasoning. We've never wrong. Neural networks get it wrong some of the time, always, right? Again, I don't see it that way. I think neural networks are great to give you very good approximations. I think they should, hopefully they should be able to make those very good approximations using less data. But I think they're very, very good to give you very good approximations. But it is true anyway that the output that you get sometimes, all the time, it is unreliable, right? And having all these extra mechanisms to be able to reason about these architectures and say, look, I know that this network does this, surely does this. I mean, with certain probabilities, with some probability certainty, does this. And why? Because I have the mathematics here. I designed it in this way, it's following these things, it's learning this stuff, I know what it is doing. So I can ensure that it has these properties. That's why I think all this symbolic machinery can really help what we currently have, not just with neural networks, with learning systems, parallel systems, and all that.
Yeah, one more, why not?
Yeah.
So where do you think industry is? Google DeepMind, AlphaFold and so on, they brought in lots of domain experts. Whereas if we look at OpenAI, for people like that, it's just scale. Right? What evidence do you see in industry form against Neuro-Symbolic take?
Look, I think we know that we can do better in many cases by having bigger systems, more data, more computing power. I think we know it. We know that if we have the luxury to have more of that, we will do better. We will do better, right? But I think there is also an awareness that it is probably too much, and that surely there is a way of finding shortcuts, of doing things that are as good in terms of quality, but with less training, with less data. And at least some people think this is one way. This is something that is not being explored fully and may deliver good results. Sometimes when you have these pressuring situations, you do very well. For instance, case of China, they couldn't have access to the best NVIDIA chips. So they couldn't train their systems using the data sets that we were using in the West. What happened? They just designed very good algorithms that could work with smaller data sets. Why? Because they have this limitation of not having access to the best chips on the market. So they were forced to do something better because of the situation. But I think even though we are not forced, because we know that we can just continue pushing more data, bigger systems, we know that that's probably not the best thing to do in the long run. We should find alternative ways of getting very good results in terms of prediction, classification, all of this, somehow using less data or something more transparent.
Great note to finish the seminar. It's actually. This is going to be our regular room for the rest of this term. So same time next week.